Hello, I'm Ed Pegg Jr., and welcome to another episode of Mathematical Games, a series devoted to the works of Martin Gardner's idea of recreational mathematics. In the 1950s, Martin Gardner started a column in Scientific American that covered uh, recreational mathematics, and it went on for 25 years, and he wrote 15 books out of those columns. But many of those items live on as unsolved problems, and one of the things that came out of the mathematical games was the Encyclopedia of Integer Sequences, which he worked. Martin Gardner had a little bit of input for uh, doing the popularization of integer sequences, and that led to a lot of new discoveries in sequences as they popularized various problems that people worked on. So one problem that got mentioned by Martin Gardner is the no three in line problem, which is in the Online Encyclopedia of Integer Sequences, sequence 769, the number of distinct solutions for a no three in line problem. Here's one of them here. Here we have a maximal solution. Notice that every row and column has two squares in it. But also, if you go through any slope like diagonals, just regular diagonals, there's no more than two. And if you do something like night moves, like a night slope, there's no more than two. In fact, for any possible slope, there's no more than 2 points in any direction. And we're only considering the centers of each of these, not the full square. You can definitely draw a line that hits 3 squares, but we're only considering the middle of these. So this is a rather cutting edge talk. For one, because last week the problem was solved up to order 70, which is a new record. But it's even more cutting edge now because 10 minutes ago, the solution was bumped up to order 72. I don't have a picture of that particular solution. It hasn't been made public yet. But 10 minutes ago, this major unsolved problem had a major update. So this is a rather cutting edge talk. So this is the largest solution for a no three in line solution with full symmetry. And this is believed to be maximal. But you can also have solutions with mirror symmetry. This is up-down mirror symmetry. This is the largest known solution with that property. You can also have double diagonal symmetry. This is reflected along the diagonals in both directions. This is the largest known solution of that sort. And here's a solution for order 65, found a few days ago. And what is it, 3 days ago? And solutions were also found for orders 67 and 69 a few days ago. And here's one of them here. And here's the largest known up until 10 minutes ago, order 70. This was the best known solution until just a few minutes ago. I wish I had the order 72 solution to show. And we can verify that there's no lines of 3 in any direction using my function find extraordinary lines. In geometry, an extraordinary line is a line with more than 2 points on it. And if you just do random lattice points, the probability that you'll find a line with 3 or more points gets to be pretty high if you have enough density on a lattice. So if we input all of these points into that function, it finds no extraordinary lines in any direction because there aren't any. However, if you if we shift everything around by mod 35, then we find lots of lines of 3. Here's a drawing of lines of 3 using these previous points. We basically we took all these, we divided it in quarters, and then we restacked it mod 35, since this is order 70. So this goes to show that this particular solution, even though it doesn't have any lines of 3, just a slight change will induce many lines of 3. There's also another problem by Martin Gardner where he asked for the minimal version of this same thing. So here's a solution with queens. Basically, you want to put queens on a board so that it's not possible to put any more queens on the board that would induce a line of 3. And when we want to know the minimal number of queens needed to block off the board from any further lines of 3. This is a somewhat well-studied problem if you just look at queens. And there's a nice paper about it, which I give a link to. This whole talk will be available on Community later today. And we have a OEIS sequence right here that gives the number of the largest grid that is possible to cover with a given number of queens. However, not as well studied as the any slope version, where you want to find the minimal number of pieces you can put on a board so that everything is blocked if you try to add any more. In fact, it's only solved up to order 10, which I thought was a shame. And there's also a related problem where you want to do in 3 dimensions, no 4 on a plane. So here are some solutions with queens. And here's a solution with any slopes. So these 8 points will block any further lines of 3. You can't put a cell here, for example, because this night slope here would go through this particular point. So since this wasn't solved for anything above order 10, I decided I would look for solutions, and I managed to find quite a few. Here's a nice solution for order 11. None of these are proven minimal, but I'm pretty sure that some of these are minimal optimal solutions. And you can see these are fairly interesting patterns. Some have a lot of symmetry. For example, this one here. I think some of these blocking patterns are quite nice. So this is a problem Martin Gardner cared about, and no one has looked at it. So I figured I would try to promote it a bit. I particularly like this solution here, and we can look at these further to kind of prove that these are actual solutions by making up a coverage diagram. So this particular pattern here, you notice that at the left and right edges, we get complete coverage. If there's a line going through it, you can basically trace it to the line that has the points. Now at the top, this doesn't have complete coverage. This square isn't present, but this is a solution for something smaller. The main point about this is that this solution can be moved left and right and still provide coverage for a smaller set than this whole thing shown here. Here's this pattern showing that it completely covers order 14. A lot of these areas have a single blockage, but others have more than one. With the 19 by 19, I was able to prove that 16 points is enough. And here's the proof. It every single circle has a line going through it. And order 24, here's the solution showing with lines that everything is completely covered. So this is a nice problem that's barely been touched, and it's somewhat easy to find nice solutions. I've got several dozen solutions here that haven't ever been seen before, and I just kind of ran some simple code to see what might be available, and all these nice solutions popped out. So this is a good problem to look at if you want something that doesn't have much competition. I also took a look at the 3D case. What is the maximal number of points you can place on a 3D lattice? And for order 3, this was a known solution here. This is provable that 16 points is the maximal. If we, for the upper end, since we have a basically 3 by 3 by 3, the maximal number of points you could place would be 9 squared times 2. So that basically every row, column, and up, down would have 2 points in it. But that's not possible. That would be 18. 2 times 9. That's not possible. And the maximal for order 4 would be 16 times 2. But you can't quite get that. The most you can get is 28 points, as shown in this position, which I think is unique. I was also able to show that for order 5, I found 110 solutions for that. This is the most symmetrical. And I was able to prove that 40 points is maximal. The high end would be 5 or 2 times 25 or 50. So this is 10 short. And then order 6, this nice solution comes out. It seems to be unique, and it's has 64 points. The maximal would be 36 times 2 or 72. So this is 8 short of the maximal. But this is the maximal number of points you can put into a 6 by 6 by 6 lattice, so that no 2 points are in any direction. And these are the best solutions I was able to find for 72, or for order 7 with 72 points, and order 8 with 88 points. I haven't been able to prove that these are maximal. The problem gets quite tricky at this point. And the function find extraordinary lines, of course, verifies that this doesn't have any 3 points in any directions. So this is a new sequence, 1, 8, 16, 28, 40, 64, that isn't in the online Encyclopedia of Integer Sequences yet. I plan to add it probably later today. But this is a nice extension of a famous problem that apparently no one had looked at. So what is the online Encyclopedia of Integer Sequences? I use it all the time, OEIS.org, and basically my usage is to, I've got some sort of crazy problem. I'm not sure how to solve it. So basically I'll look at the smallest examples and try to convert it into an integer sequence. And after usually making 5 examples, the simplest 5 examples, I've got a sequence I can look up, and more often than not, there is a sequence in the database and it has a full description of what's going on. One thing that also can happen is you do that process and you come up with something that seems completely unrelated to what you're looking at. And quite often there have been cases where a interesting proof has come out that this strange thing is related to this other strange thing. So it all started in 1965 when Neil Sloan decided to collect integer sequences on file cards that he put onto computer punch cards. And at Bell Labs, he completed a manuscript for a handbook. And Martin Gardner mentioned it in 1974 that this was a great book, and he wrote a column about it. Later, Neil came up with a website at Bell Labs, and he launched it with 10,000 integer sequences. And a few years later, he announced, when Bell Labs was kind of trying to get uninvolved with it, Neil Sloan wrote to the mailing list that he wanted to get a site and was looking for suggestions. So I told him, OEIS.org is available, you should buy it. And he did. And so that's how the sequence, how it is at OEIS.org now. So I thought I would talk about some examples of famous sequences in the online encyclopedia of integer sequence. And we may as well start with one. The sequence number one is the number of finite groups. And we've got a demonstration on that. These are the number of groups of a given order. And the next one is somewhat strange, the Kolakowski sequence. A sequence over 1, 2 that is equal to its own run length encoding. So that basically means that there's 1, 1, 2 2s, 2 1s, a 2, 1, and then 2 2s. Well, if you look at the run lengths are 1, 2, 2, 1, 1, 2, 1, which is the same as the sequence itself. This is a strange pattern, and here's what it looks like if we look at the first 60 squared terms. We get this pattern. Number of divisors is a classic sequence, and the sum of divisors. I also notice the divisor sigma function, and we can take a look at different plots of these. There's a number of divisors, and there's a sum of divisors, which comes up with a strange pattern. Sum of divisors squared. And I forget what happens with Gaussian integers, yes. So a rather strange looking sequence. We can, all of these functions have various ways of computing them, and here's 2 different ways. And the next would be partitions, the integer partitions in which no part is repeated. We have more partitions later on. So these are partitions where nothing is repeated, and it's equivalent to the number of partitions into odd parts. And this basically has a demonstration for why that works. Odd and distinct. Here's 2 different ways of computing it. We can just count the number of integer partitions, but there's also a series representation for the same thing. And it's a rather simple, it's 1 plus x to the k will give the product of that will give the same series. The other totient function counts the number of positive integers not exceeding n that are co-prime. So, for example, with 8, the numbers 3 and 5 are not co-prime to 8, and also 7. So here is a plot of the function. and we can take a look at various items within the list. Bracelets, the number of different strings for putting beads on a string. Here's different. There's 51 bracelets with 5 beads of 3 colors, and this will show all the various bracelets of that form. We can also say look at just 2 colors, and there's 8 different bracelets with 5 beads and 14 with 6. And these are the different bracelets of 6 beads and 2 colors. And 130 of 6 beads and 3 colors. And these are different pieces of code for counting the number of different bracelets of a particular type. The Lucas numbers are equivalent to the Fibonacci numbers, but they have a different start. Instead of starting 1, 2, they start 2, 1, and then they add progressive numbers. The Lucas numbers and Fibonacci numbers are closely related. Here's a series representation, and since it's based on the sum of previous terms, it's a linear recurrence. We have a Lucas L function that calculates it directly. This is 3 different ways of calculating the code. If we stack all the terms in their binary representations, we get these strange triangular patterns once they're put all next to each other. And here's a study of different starting positions for similar sequences and how they behave. The prime numbers, I'm sure everyone knows. We can make a spiral out of them and label the points 1, 2, 3, and so on. And this was something Ulam did in what he described as a boring lecture. And Martin Gardner wrote a column of this, noting how a lot of primes aligned on diagonals. Something a bit stranger happens on a triangular grid or a hexagonal grid. We get 3 distinct patterns pointing at the center. And of course, here's a table showing the sieve of Aristophanes. And I think at 12, things get interesting. At 12, everything collapses to 4 columns, and at 6, also past the first row, everything is in 2 columns. Partitions are the number of different ways of dividing up an integer. For example, with 8, you can divide it. You can just leave it as 8 or 7 and 1, 6 and 2. These are all the different partitions of that integer. And the series representation, this could be simpler, is this interesting product. So here are the partitions for 9, and we could show these as stacked columns, which I think is an interesting pattern. And while I was putting this together, here's the pattern for 14. I wondered what the minimal number of horizontal lines would be. And that led to a new sequence of sorts. This is the minimal number of lines for partitions of 7. You can prove that you need at least, 1, 2, 3, 4, 5, 6, 7, 8, that you need at least 8 lines to represent all the partitions of 7. And I think we solved this up to partitions of 13. We can also use Euler's method for generating the partitions, but it's a rather complicated method involving polynomials. And once you multiply these out, you start getting the number of partitions appearing in the polynomial. And as you get more and more complicated polynomials, you get more and more terms. The plot of the binary representations looks like this. The Fibonacci numbers, you add previous terms together. It's very similar to the Lucas numbers. Here's 3 ways of doing it. The series representation is based on this polynomial. And we can get a nice golden spiral out of it. Here we're basically putting arcs into the squares, and then we just start making squares based on the Fibonacci sequence, and we can just zoom out to give a Fibonacci spiral. Which I thought was interesting. This is the pattern that comes out if we stack the binary forms of the numbers. And we can take a look at the Fibonacci numbers in terms of domino tilings with, let's see, right, let's go to order 6. For order 6, there are 13 different ways of tiling the figure with dominoes. And for order 7, there are, or for order, yes, that looks like it's 7. I wonder why it says 6 up here. Anyways, the number of solutions for the domino tiling is a Fibonacci number. And there's a formula here found by Catalan in 1961. The order 2 terms are the Fibonacci numbers. But in terms of, if you look at the number of order 3 tilings, so 3 by n, there's this many solutions, which is also another sequence. If you look at 4 by n, the number of domino tilings is this sequence. These enumerate the number of domino tilings for a MN rectangle. Fibonacci numbers add up the previous 3 terms. And these are related to the number of ways of going 1, 2, or 3 steps up a stairway. So it basically shows it here. 149 is one of the Fibonacci numbers. And these are the different combinations for going up just 1 at a time. There's 8 ways of going up everything 1 except 1, 2. 21 ways of 5 1s and 2 2s. If you look at the number of combinations, if you make all these different permutations and add and do a total count, you get that there's a total of 149 ways of going up the stairs if you go up 1, 2, and 3 at a time. Powers of 2 and powers of 3. So they start out pretty easily, 1, 2, 4, 8, 16, and 1, 3, 9, 27, 81. Here's different ways of calculating the 2 to the n series. This is the generating function. If we look at the number of subsets of 5, there are 2 to the 5th subsets, as shown here. And we can do the different powers for different numbers. The involutions are permutations that are equal to their own inverse. So for example, this is an involution. If we do this permutation twice, we get back to 1, 2, 3, 4, 5, 6, 7, 8, 9. The total number of involutions is given by this formula. So there's 1, 1, 2, 4, 10, 26, and so on involutions. And I thought, as a challenge, is it possible to make a Sudoku with nothing but involutions in the rows? And I came up with this solution. It also has the property that there's no repeated digits on the diagonals. And also along the red line, this is what's called a German whisper. Terms on this line differ by 5 or more. And this is a completely solvable Sudoku puzzle. If you go to this link here, you can try solving the puzzle yourself. And this is a rather easy Sudoku because of the involution property. Because, for example, if this cell here was a 1, you'd know that this cell here would be a 5, because every pair of numbers on the row will point to itself. And on each row, there's also one digit, which is basically its position. Like this might be 7, which is also the 7th position. So this Sudoku puzzle of involutions, even though it was very difficult to set up. In fact, I believe if you have the diagonal property where all the diagonals are distinct, the solution is unique. But that wasn't a very solvable puzzle. I tried various ways of trying to solve it, but all of them involve some rather horrible logic, and it just wasn't a human solvable puzzle. But with this German whispers line, it's a rather solvable, easy puzzle. Free pentominoes. This code here will give the number of different pentominoes or polyominoes. There's different types of polyforms. And this particular shape here, one of these shapes is, I think, the hat. Let's see, that's order 6. I think it's order 5. Is the hat in there? I think so. I've already forgotten what the hat looks like. How embarrassing. Might be that one. But when I came up with this years ago, I was thinking of trying to find out what the tiling was for all of these various shapes, but I never got around to it. So somebody else found the hat first. The Catalan numbers. These are different ways of counting steps in a lattice. Here's the generating function. So we can look at equivalent Catalan number representations, maybe with fewer signs. So there's 2 ways of dividing up a square by diagonals, and also doing a Steiner tree. So with a pentagon, there's, I think, 5 ways of dividing it up in diagonals. And there's also various other things going on in this for Steiner trees and whatnot. The hexagon has more inequivalent forms. So there are 14 different ways of dividing up the hexagon into diagonals. So it looks like there's also 14 different Steiner trees for those 6 points. And I've forgotten what the parentheticals mean. And with the heptagon. There's also a staircase representation for the Catalan numbers. And there's a Catalan number of different stair steps. We can also do Catalan trees, as shown here. The Bell numbers are related. They're the number of different ways of partitioning into different lines and blocks. I think 15, right? So these are different Bell number patterns. The zigzag numbers count the number of alternating permutations with up-down or down-up orderings. Here's a series representation, and here's a demonstration of those permutations. They all zigzag. So there should be 61 different at order 6, and these are the 61 zigzag permutations. With the lazy caterer sequence, you basically want the maximal number of pieces just by making slices. The rule is that every line has to intersect every other line without any 3 meeting at the same point. That will make the maximal number of different pieces. And it turns out to be a linear recurrence. By summing up previous terms, you can get what the next term is, but it's slightly complicated. The Pell numbers approximate the square root of 2. If we look at the convergence of the square root of 2 and look at the denominators, we get the same terms. And these are also a variety of the Fibonacci numbers with a slightly different linear occurrence. Here's the generating function. And these are the Pell numbers that fall under the law of eponymy, which is that almost everything is named after the wrong person. So this is the Pell equation that was studied by Archimedes and Brahmagupta and solved by this guy, and later looked at further by Fermat. And Ron wrote a book about the problem that included a solving method, which was translated by John Pell. All he did was make a translation. But Euler thought that Pell solved the problem, so he named this whole problem after Pell, because he thought that the translator was the solver. So this is an example of why a object in mathematics got misnamed. So Lagrange came up with a method for solving problems of this sort, and some of these problems have enormous solutions. So let me see if I can find something with a more reasonable value. So something like 58 has a more reasonable solution. And this is the enumeration of solutions. All right, so I think So 4 has 20 solutions. I think that might be a different sequence I'm thinking of. But these are the different Pell equations. Maybe 5 is the smallest, right? These are the smallest values. So the next one should be 12 here. Or maybe not. That's 7. Yep, I'm not sure exactly what's going on with this. Somehow this is related to the Pell numbers, but I think that's a different sequence I'm thinking of now. The factorials are easy. You multiply all the numbers up to n. The arrangements count permutations with no fixed points. And there's a hat problem that deals with derangements. Here's 2 different ways of calculating them. These are also known as the subfactorials. And we can plot the derangements. Basically, in these diagrams, no vertex points to itself. So you get nice different patterns because there's no loops in them. In Queen's problem, we basically want all the solutions for putting queens on a chessboard so that there are no more than 2 queens in a row, column, or diagonal. You can't do this with all slopes because as soon as you placed one point, any other point anywhere would have a slope with that other point. So that's why there's no single point version for the no 3 in line problem. Just because, yeah, with any slope, you basically rule out everything. Triangular numbers. As a teenager in the 1700s, Gauss proved that every integer is the sum of 3 triangular numbers, which was an unsolved problem. So this was a nice start to Gauss's career to solve this particular problem. And he made a note that Eureka, any number is the sum of delta, 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 which basically means 3 triangles. And we can show that here. Oops, I'm not quite sure why this is saying 6.25. I probably have a variable hard set, but this is at least showing the different triangles. How many solutions are there? We can solve that, and we can plot out the number of different solutions for each integer. Mersenne numbers are of the form 2n minus 1. If those numbers are prime, then you have basically a famous largest prime number usually. For most of human history, the largest known prime number has been a Mersenne prime. But not all. In fact, these are the known Mersenne primes here. If you use these exponents. And here's 2 different ways of doing the basically non-primes, just 2n plus 1, or we can use this series. Most Mersenne numbers up to 2 to the 1,200 have been factored. So we want to use the minus sign. Usually they are more interested in the to the n minus 1. So here's a factorization of 2 to the 967 minus 1. So this is a long-term human problem. These numbers are of general interest in computer research. So factoring all these numbers has been a priority for solving other combinatorial problems. For example, I forget what the problem is. I can't remember. I'm blanking on what it is. But if you have all these factorizations, you can calculate a particular object in combinatorics. I'll probably remember it a little bit later. But with these factorizations, you can calculate these items, and there's strange patterns if you convert these numbers to binary. Let me see if that was one, wasn't it? So for example, here's a number that factors in an interesting way. This last number is basically all ones. And we can also look at the plus ones that have also been factored. Square numbers. There's a simple proof that all squares are the sum of odd numbers. Tetrahedral numbers. Here's a representation in layers. Square pyramid numbers. Pretty much the same thing. We can stack rhombic dodecahedra to make a square pyramid. Perfect numbers, abundant numbers, and deficient numbers. When the sum of the divisors minus the number of self is equal to the number, such as with 6. 6 has the divisors 1, 2, and 3. Sum those together, you get 6. 28 is similar. If we go if it's greater, if the sum of the divisors is greater, then it's a abundant number. Otherwise, it's a deficient number. So this shows the pattern of perfect numbers. I forget what the next perfect number is. There it is. This is a pattern of perfect, abundant, and deficient numbers. Cube numbers. We can basically look at the cubes. And for each one of these, I'm trying to show a generating function if one is known to exist, because I wanted to compare what the generating functions look like. Ordered Bell numbers are also known as combination lock numbers, because if you have a door with combination buttons where more than one button can be pressed, you can calculate the number of combinations where each button is pressed once. So for 3 buttons, it's 13. The Padovan sequence here's the way of calculating it here. I believe this is related to the Narayama constant. So yes, this is somewhat related to the Fibonacci spiral. So here's the Fibonacci numbers here. And I had a curved version earlier. So basically we can keep adding squares to get a bigger and bigger spiral. If you go to 3 dimensions, we can start with cubes and then add a domino and then a new cube, and continue with that method where we keep on adding larger and larger cuboids, and we get the Padovan spiral in 3 dimensions. So these are the Padovan spiral numbers. Lucky numbers is a different way of using a sieve. Basically, we begin with the odd numbers, then repeatedly delete every kth number where kth is the next survivor. This is similar to the prime numbers because we're using a sieve, but these are slightly different because the lucky numbers diverge. The number of solutions for the Chinese ring puzzle is given by this sequence. And here's a solution that uses the binary gray code. Motzkin counts the number of paths to a particular lattice where we can go up or down, but you can't go below the line. So this is the number of different paths of that sort. Self-avoiding walks, we basically do a walk. Let's see if I can get a reasonable number here. These are randomly generated, but for order 8, I believe there are that many different walks where you start from the origin and never visit the same vertex twice. This counts the number of walks of that sort. Heron is related to the Padovan sequence, which is also related to the Nirayama constant. It's a different starting point, and it has a different generating function for its series. There's a complicated way of relating the Perrin and Padovan, the numbers relating to unusually complicated polynomials, and this gives different polynomials related to those functions. And with those polynomials, multiplying them together and coming up with a particular interpretation, you get either the Padovan numbers or the Perrin numbers. Centered square is the number of basically black squares on a checkerboard, and each square has a -1 for what the white squares would be. It's either the same or plus minus or -1. The Deloy numbers count particular paths through a grid. And these are also able to make carpets of various sorts based on the modulus. Pronic numbers are basically n times n plus 1. So easy to calculate. There's the generating function. The rectangle made by these products, 2 times 1, 3 times 2, 3 times 4, is what's known as an oblong. And these are difficult to divide into squares usually. These are different solutions for dividing up the oblongs with a minimal number of squares. Central trinomial coefficients are mapped out by the Pascal tetrahedron, and we can look at different moduli, and we get different patterns, much like we get different patterns in Pascal's prime for different moduli. The diatomic sequence is based on Calkin-Wilf fraction. So for any number, there's a Calkin-Wilf fraction. So this is a resource function that gives these fractions. So 1, 1/2, 2, 1/3, 3/2. If you look at the numerators and denominators, you get this sequence and this sequence, but they are equivalent except that this sequence just has 1 at the start. So this is a way of enumerating all the different fractions. And here's a tree showing how these fractions are related to each other. This is also known as the Fusk sequence, FUSC, or this Stern-Brokat sequence. And here's what a plot of these numbers looks like. It's a rather strange pattern. So for any integer, we can get either the Calkin-Will fraction or the Stern-Brokat fraction. And this is just an example of the 75th million fraction is right here. Ulam numbers start with 1 and 2. Each new term is the smallest integer having exactly 1 representation. So these are examples of those. They grow in an unusual way. Lothian numbers are the numbers of this form, x squared plus xy plus y squared. Simple to calculate. These give the 3D equivalent of Ford circles. So if we calculate, if we start with circles of a particular, or spheres of a particular form, and then look at the tangent spheres, we get spheres of a particular curvature, which is 1 over the radius, and all of those curvatures are Lothian numbers. Binary reflected gray numbers are based on the bit XOR. These have the property that every neighboring term is only 1 different in binary than the previous term, which is a good way of, if say you have a satellite tracking the magnitudes of stars, and you have a slot for the different measuring the light intensity. If you just use binary numbers, you can get wild swings between terms. But with the binary gray, all the changes as the starlight goes across the sensor is a nice smooth pattern. So these are actually used in things like light detection. The square free numbers are based on, can be calculated with the Mobius move function. And we can plot these. Zeta zeros can be, with the zeta function, can be used to calculate some of these. It's a very difficult way of calculating something that's actually easy to calculate, but sometimes using these different relationships will lead to interesting techniques and other functions. The Recursive function, at step in, try to subtract in, and if those go negative, you add 1 instead, and that leads to this unusual sequence. Shown here, which has all sorts of interesting arcs in it. Here's what the plot of the Recursive numbers looks like. Look and say sequence, 1 1 1 1 1, 2 1s, 1 2 1 1. Basically, you look at what's given there, and you basically just say what you see. This is a unusual sequence because Conway managed to show that this was related to an order 70 polynomial. Fairy sequences represent all the fractions, and if we plot all these different fractions and then look at the gaps between them, we get this unusual curve between them. And this is the number of different terms in the Fourier sequence. Josephus numbers in the Bible, Josephus was trying to survive a practice where they would just kill, put people in a circle and then kill every nth person until there's only one left. But he solved the math, so he knew where in the circle to stand. So they're called Josephus numbers. And these are, this is a sequence where for different starting points and different gaps, you can get what the survivor would be. Schroeder numbers also count paths. Stopping times for each Collatz number. Basically, you have, let's see if I can label these. Oops. For each number, you either divide by 2. I forgot how the Collatz works. You this is how the basic chains work. What numbers connect to each other in the Collatz sequence. What is it? Multiply by 3. Oh, I should probably know that. Pascal's triangle. In different moduli, we get different patterns. And we can plot out the different numbers in Pascal's triangle, and we get this strange term if we make them as binary stacks. This is the same thing in ternary. We get these strange patterns. The Stirling numbers also has a point diagram as shown here. And the second kind has a related diagram. 25 terms is here. The Eulerian numbers counts the permutations according to their number of ascents or descents. So let's see if I can remember how this works. Eulerian numbers versus Stirling numbers. So this basically breaks down how these various numbers will fit together with ascents and descents. A Mobius function is 0 when n has a squared prime factor. Otherwise, it's a sign related to the parity of the number of prime factors. And this is a random walk based on these Mobius functions. Thue-Morse sequence gives the number of ones in the binary expansion of n, and we can also generate with a substitution function. So this gives the pattern of the Thue-Morse sequence when we combine these two items. The paper folding sequence is the number, if you repeatedly fold a strip of paper, we get this particular sequence. And as we change the angle, we get different patterns for how the paper is folded. The De Bruijn sequence has all, in the partitions, have all digits. So for example, here's a de Bruijn sequence of order 5. So if we look at every group of 5 in sequence, we get these numbers, which we can show here. And if we sort them, we get the binary sequence. And if we add arcs, we can get unusual patterns for how these functions fit together. And this gives the number of different de Bruijn sequences exist. The Baum suite sequence is, the term is 1 exactly when the block of consecutive zeros in the binary snapshot has even length, and we get this strange pattern. Mondrian art problem. Partition an n by n square into multiple non-congruent integer size rectangles. So, oops. Not sure why that's not working. It wants to stay at 60. It got, oh, here we go. So order 4 square, these are ways of dividing up, for example, order 6 into different rectangles where nothing is repeated. That's the variant though, non-congruent, but it can repeat if it's in the other orientation in this variant. Here, no rectangles are repeated in either direction. And the question is, what's the minimal for the largest minus the smallest? So the largest here is 9, the smallest is 4 with a difference of 5. And it's an open question whether it's possible to divide a square so that the minimal difference is 0. So here's a more complicated case. These are the best known solutions. This has been proven up to order 70, I believe. So I started with the no 3 in line, the Martin Gardner minimal variant. Here's some nice solutions for that, but none of these are proven to be maximal. For example, can someone prove that this is 20 points on the 24 by 24? If anybody can prove that that's minimal, that would be interesting, and we could probably extend this particular sequence here. And that's the conclusion. This notebook will be available later at community.wolfram.com. Many thanks for listening, and I'll be glad to answer any questions that may have popped up. Let's see. Yes, the notebook will be available later. And that's the end of my talk. Many thanks for listening.